Okay, this is an experiment in showing you how to solve a large analog puzzle. This is typical of one of the little examination papers that we've set. So what we're going to do now is we're going to have a look at how we would actually work through this design. Well, let's start over here. This part of the circuit is a straightforward differential amplifier, so that's the diff. I'm going to postpone actually working on the diff. First off, I'm going to work on this part over here, and this part is a reference cell for a current source. So this is effectively the reference side of a current source. Okay, let's just have a little note about one or two specifications. A couple of things on my circuit diagrams as well which are quite useful. The spec. I've got a supply voltage here of plus and minus 3.6 volts. So the supply is 3.6 and minus 3.6. Okay, I'll put plus on there. So you've actually got two voltage rails to think about, which is important. I've got one transistor, and I'm giving you the parameters here. Beta 255, reverse saturation current 14.34, 10 to the minus 15, early voltage VAF 74. Your spec. I want 0 volts DC coming into the bias of the differential. Okay. The tail current in the differential down here I want to be 2 milliamps. Okay. The reference current down this line here wants to be 0.5 milliamps. Okay, and that reference current should also be copied down here as well. So there's two reference line currents in this circuit design. The output stage current comes down here, and that should be again 0.5 milliamps, and that's I out. Okay. I want a differential voltage gain of 20. So V out AC here, and the differential input should give me 20. Now, it's only got a single-ended output, and this is differential mode, so you're going to have to double that gain to get your circuit working. VAF improvements, which will help you start to calculate degeneration around here and around here, are set to 10 to 1. You have to design all of these, and we're doing it using parameters inside ORCAD, so we don't need to change anything on the schematic. Once you've done that, I want you to measure the common mode gain, the differential mode gain, and then the common mode rejection ratio. So let's split this into tasks and then work out how we can design it. So let's start here. This is probably the best place to start, and this is the current source. So we're going to want a reference current down here of 0.5 milliamps. According to the reference current design, there'll be 0.5 milliamps down here as well. We've got 1, 2, 3, 4 degeneration resistors that are going to improve the performance of this circuit. Well, let's just go back to our bit of maths. VAF effective is equal to VAF into 1 plus VT over VE. Okay. Now in this case we know that we want a 10 to 1 ratio, so VAF effective should be 740, VAF is 74. VT we don't know, but we can rewrite this expression as VAF into 1 plus RE over, and I'll label it RDEG1, okay? So those degeneration values are already done. So if we do that, we've got 740 equals 74, 1 plus RE over RDEG1. Simple bit of maths, we now then can do RDEG1 is equal to RE times 9. Okay, RE is VT over IE. Okay, and VT is 25 millivolts, and IE is 0.5 milliamps times 9, 450 ohms. Okay, so we have now designed this component, this component, this component, this component. Point to note, these are a PNP mirror, and technically I should have used the parameters for those transistors. The parameters that I gave you are for the NPN transistors down the bottom here, but I'm just abbreviating it. So these two resistors should have a slightly different value of emitter degeneration. Doesn't matter in this case. Here we've got a couple of ballast resistors. Now all their job is to just provide a voltage drop from the top to the bottom. Otherwise we might get a little bit of heat generated, or a little bit of stress on some of our transistors, and that would give us an early voltage issue, certainly around Q7, where VCE would affect it. So I'm just ignoring that for the moment because of these two ballasts. So we've designed our first component. Now let's design the most crucial component. The most crucial component is the reference current resistor. Okay. Now this one's quite important to get right. What we need to do is to calculate the Kirchhoff's voltage loop around here. Okay, that's the KVL that we're looking for, just there. So let's write it out just down the side here, and then we're going to go over the page and put that through. So we've got I reference, okay, R degeneration, plus VBE Q6 is equal to I reference, RI reference, okay, that's this resistor here, plus I reference, R degeneration 1. Okay, there's our expression. Now if we know what we can cancel, I ref R degeneration 1, I ref R degeneration 1, that cancels. We're now left with VBEQ6 equals I ref R ref. Let's move on. VBE Q6 is equal to I ref RI ref. Okay. VBE Q6 is VT natural log I ref over IS is equal to I ref RI ref. Divide by I ref. We've now found RI ref. So let's put some numbers in. VT 25 millivolts, natural log I ref 0.5 times 10 to the minus 3 divided by 14.34 times 10 to the minus 15, all divided by 0.5 times 10 to the minus 3, should give me the value of RI ref. Okay, quick maths, I think that's 1213 ohms. Okay, so we've now calculated our reference value. We might want to do some optimization on that value, but we'll do that in a moment. Now let's go to our tail current. Okay, so we've got various outputs to this. Now our tail current, let's just draw this circuit. Here we are. So this is minus VEE. This is RT. This is IT, the tail current, and this is our I reference or I out, because it would be the same thing. Okay, and this one is Q4, this one is Q6, and this is our degeneration 1. Well, if we went around that Kirchhoff's voltage loop, we've now got different values of RT to create our different current loop. So there's our Kirchhoff's voltage loop. We have IT, RT, okay, the volt drop provided by the tail current over RT, plus VBE Q4 is equal to VBE Q6 plus I reference R degeneration 1. Okay. Well, what do we know? Let's play the what do you know game. VBEQ4, you can calculate the value of VBEQ4 for 2 milliamps. VBEQ6, you can calculate the value of that transistor for half a milliamp. You know the reference is half a milliamp, and you know the degeneration resistor, 450 ohms from previous page. we know the output current 2 milliamps, we can calculate RT. So with a little bit of manipulation we can simply write RT is equal to, I'll write this out once and then what I'll do is I'll put in all the numbers, okay, that I've calculated. I won't put in all the detail, you can do that yourselves. So VBE Q6 plus IREF R degeneration 1 minus VBE Q4 all divided by IREF. Sorry, IT. Okay, if I put the numbers into that, okay, now this would be VBE Q6 is VT natural log 0.5 milliamps over 14.34 10 to the minus 15. I made that 0.6068. If I add into that the degeneration, 0.225 volts, and I subtract from that 0.641, which is VBE at 2 milliamps, and then divide that through by 2 milliamps, I find RT is equal to 95.43 ohms. Okay, so I've now calculated my resistance for that part of the circuit. So we've now designed all of our current source elements. Okay, we've got everything we need. We've got the reference resistor, I'll just put a little label on there actually, RI ref. Okay, so we've got our reference resistor, we've got our tail current resistor, and we've got our degeneration resistor. Now what we need to do is to design our differential amplifier. Let's put some of the specification on here, just so that you're aware of what's going on. This was 0 volts DC, okay, that's at the same point. Our collectors was at 1 volt DC, okay, that was part of the spec. Okay, it says don't change these resistors, the base resistors, they're basically the input, a function of the input impedance. Okay, so we want to leave them alone. We've just designed this element here, and this is now a current source pulling 2 milliamps. Okay, so we don't need to think about that one, we can just call it IT. Well, very, very simple now to calculate our RC. Remember, this is VCC, and that is at 3.6 volts. Plus, down here we are at minus 3.6 volts. Okay. RC, the value that we need here, can very simply be calculated from VCC minus VC, the absolute potential here, okay, for DC, we'll call it VC, all divided by our collector current, and our collector current is IT over 2. So we have 3.6 minus 1 over 1 milliamp, okay, 2,600 ohms, 2.6K. Really simple to calculate. Now let's just remember our ADM specification. Our ADM was 20. Now in this case we have a differential signal coming in and we only have a single signal coming out. Okay, so ADM would be a differential out of a differential in, so we're going to need twice that value. So our ADM that we're going to use is effectively going to be something like 40, because we're only reading half the signal. We're only reading this half, not this half from the other side. Okay, and that's different. So ADM in our case, like we say, is V out internal minus 0 volts over V diff A minus V diff B. So the voltage at these two nodes. So you can clearly see that here we've got a signal in phase, out phase, in phase and ground. So we've only got half the gain than what we'd expect. So that's why we're doubling our ADM to 40. Okay, so let's do a quick calculation then. We need ADM should be equal to small signal equivalent model. I'm forgetting the signs here because we're using phase correct signal output. 2RE plus 2, and we called it on your circuit RD. That stands in this case for degeneration of the emitter. So I suppose really I should put modulus there just to make sure that we know that we're dealing with just absolutes and not phase inversions or anything. Quick rearrange of that equation. We can now calculate RD by rearranging. Okay, and that will be RC over 2 ADM, okay, minus RE. Okay, let's put some numbers in. We've got 2,600 ohms, all divided by 2 times 20, okay, because we're only reading the one side, and subtract from that RE. RE is 25 millivolts, okay, over 1 milliamp, so that's 25 ohms. So what does that equal? 65 minus 25 equals 40 ohms. Okay, so we've calculated our value of the degeneration component RD on the circuit. We've now got basically the gain designed, the amplifier designed. The only thing now is the output stage. Now if you looked at the output stage is formed by a DC level shift. Okay, so here we would have 1 volt DC and we want 0 volts DC. This is a current source and it's using the same degeneration, so this is pulling 0.5 milliamps, okay, as per the spec. This is at VCC, which is 3.6 volts. Has no effect on this design, and this is at minus 3.6 volts VEE, and again has no effect. Let's just write out the Kirchhoff's voltage loop for the input through to the output. The output is labelled as Vout. Let's label the input as VC. Okay, that was the absolute DC voltage at the differential. So Vout is equal to VC minus VBE Q3 minus I out. Okay, this label down here was I out, this current source. So I out RDC. Let's think about what we know. This voltage here, V out, we know it's a specification 0 volts. VC is a specification 1 volt. VBEQ3 we can calculate because we know the current. Okay, I out we know, RDC we can calculate. So let's rearrange. RDC should be equal to, V out was actually equal to 0, VC was 1 volt, so we can simply add that to this side and then subtract or divide through. So that's VC minus, I'll put in the detail, VT natural log I out over IS. Okay, so that's VBEQ3, all divided by I out. Okay, put some numbers in. 1 volt DC at that node, 25 millivolts, natural log 0.5 milliamps over 14.34 times 10 to the minus 15. Okay, all divided by 0.5 times 10 to the minus 3. Okay, the value that I've calculated for that one is 786 ohms. Okay, so we've now got the whole circuit designed. Okay, so we should have everything ready to go. We've got all the maths done, and that didn't take too long. Now what we'll do is we'll put those numbers into OrCAD. Okay, as you can see, I've just summed up all of the values here. These are all the calculations. What we're going to do is we're going to pop them into OrCAD, and then we'll do some DC sweeps, and we'll find out what the optimum value should be. Because sometimes, you know, when you actually do a design, it doesn't quite work exactly the way you would expect. So we're going to recalculate and see what happens. Okay, I'll keep those edits. And I'm continuing recording, so let's go to OrCAD. Here we have OrCAD running, and we have that design inside. So let's put all of our parameters in place. Let's start off with our degeneration resistor. That was 450 ohms. Okay, our reference resistor was 1213 ohms. Okay, so that's this one and our reference line, and our two at the top. The degeneration, the output stage, was using the same current, so that's the same value. Let's put in RT. RT was slightly different, and that was calculated at 95 ohms, wasn't it? 95.43. Oh, wrong one. 95.43 ohms. Our collector load resistance was 2600 ohms. Our degeneration resistance was 40 ohms. And our output stage resistance was 786. Okay, so we've now put all the numbers that we've calculated on this circuit, so I'm now just going to perform a basic bias point. Popping up here, bias point is set up, click OK. Hitting simulate, OrCAD will run the simulator, nothing is displayed. We go back here, we can now turn on the voltages and the currents and find out exactly what current is flowing inside our circuit. So, our reference resistor, or our reference current, is 544 microamps instead of 500. So we obviously need to optimize our Iref to bring that down. Our emitter current, our tail current, 2.18 milliamps. It's a little bit hot, a little bit too high. So when we reduce this and we optimize this value, we should get closer to the spec. So my first optimization is going to be to change Iref and see if we can improve our reference current in Q6 from 254 microamps to 500 microamps. So we'll get it exactly bang on where we want. Let's go to our simulation. We're going to do a DC sweep. We're going to change the global parameter, in this case RIREF. Okay, that's the name that's been given on this parameter down here that you can see. This parameter, RIREF, it's nominally 1213 ohms, so I'm going to start it at 1k and I'm going to run it up to 2k with a 1 ohm step. I'm hitting save again, and now I'm going to hit simulate. Notice I've only put one current source on here, and now we actually have a curve that we can depict. We want to pick off 0.5 milliamp. Okay, so we can use the cursors, roll down and pick off a value here. We can see that we are very close to our 500 microamps there. Okay, and we're pretty close, within 1 microamp. What I'm going to do now, I'm just going to do a little bit more advanced way of measuring those values rather than just using the cursor tool. I'm going to go trace, evaluate measurement. Okay, I'm going to say down here we want x at nth y. Okay, and the first value is the function, so I want the collector current ICQ6. The next parameter is the value, and we want 0.5 milliamps, and we want the first occurrence of that value, 1.30761k. Let's go back here, 1307.6 ohms. Okay, click save. What I'm going to do now, I'm going to edit my simulation profile. I'm going to go back to a bias point, click apply, click OK, save again, resimulate. Okay, minimize that. We can now see, look, my collector current is 499.9 microamps. Okay, very, very close to 500. Okay, so to all intents and purposes, that's bang on. I'm now going to go and check my tail current source. It's at 1.99 milliamps. It's a little bit out, so I'm going to optimize on RT. Okay, it's at 95.43 ohms, so I might go from 94 ohms to 90 ohms to 100 ohms or something like that. So I'll move this current probe. I'm going to move it here, and I want this to be 2 milliamps exactly. Okay, DC sweep, global parameter, this time it's RT. Let's go from 90 ohms to 100 ohms, and let's go in 0.1 ohm step. Okay, now you notice it's gone a little bit jagged here. Simulation accuracy has fallen over. It can't quite qualify the difference between the two. That means we need to change the relative tolerance in the simulator. So let's go back here. Options, rel toll. I'm going to add 1 order of magnitude into relative tolerance. Okay, hit save, simulate again. The number's gone, nice smooth curve. Again, it's just one of those expert uses of that rel toll. I could use the cursors. I'm going to use my evaluate measurement. Okay, again I'm going to use x at nth y, and we're looking this time for ICQ4, and we're looking for 2 milliamps, and we're looking for the first occurrence of it. 94.93 ohms. Okay, so let's go back to here. 93.94 ohms. Hit save. Let's go back and go back to bias. Simulate again. Back to my circuit. 2.019 milliamps. I'm slightly over, but again, very good. I'm very, very close to my specification. Let's have a look at what's going on this circuit now. We've got 1 milliamp in the collector for here. So now we've effectively designed the current reference. Now we need to design the differential amplifier. At the moment we've got COM A and COM A. So this would be measuring the common mode gain. Well, I don't want to do that yet, so I'm just going to change the label on this wire to diff A, and the label on this wire to diff B. Okay, so that's the differential 10 millivolt signal is going to come into this circuit, and we want to measure the common signal coming out from V out down to ground. So differential signal in, common mode signal out, and we're going to look at what the gain is. The gain should be set to 20. Our differential gain ADM should be 40, and this should be set to 20 in effect the way it's working. Now I'm going to cheat slightly here because I've already got a few circuits ready, or a few equations ready to do my measurement. Transient, 10 milliseconds, 5 microseconds. I'm now simulating. I know it's at 1 kilohertz. I'm going to get 10 cycles of a sinusoid. So I can go and take that back off my circuit now. Don't need that. What I'm really interested in is the differential signal in and the differential signal out. So I'm going to use the differential voltage probe. Okay, diff A, diff B, and I'm going to look at the signal across the differential amplifier. Okay, so this should be a gain of 20. Let's see what's been plotted. Green is my input signal and red is my output signal. Okay, I'm almost at 400 millivolts. Okay, and my input signal is wherever. Let's have a look at where my signal is. If I go here, which is about the peak, okay, and if I put this one on this side, okay, we can measure. We've got 10 millivolts and almost 40 millivolts, 400 millivolts. We've got 376 millivolts. So we're very, very close to our gain of 40 in this circuit, which would give me a gain of 20 when I am taking half of it out. So what I now need to do is I need to optimize to get the gain to hit the value that I want. The value that I want is a differential gain of 40, okay, and then I can optimize my output. However, now my output isn't taken from the differential amplifier. My output is taken from V out down to ground. So let's delete that component and let's plot this value down to ground. Okay, now there is a small DC shift here which we haven't moved out, which is fine, because what we're going to do when we're going to calculate the difference signal, we'll only look at the peaks and the troughs. So we'll actually get rid of any DC component, and then we can actually extract the DC component later when we optimize. So, looking at the peak and the trough of those two waveforms, here's how we can do that. Well, you remember me saying that I'd actually optimized and I'd labeled all my circuits. Well, I've written out the differential signal at the input, the differential signal at the output, and I'd also written out some min and max values. So I can calculate here, using this equation, the maximum voltage out minus the minimum voltage out. If I subtract the two, I get the peak to peak voltage at the output, okay, which is what I want. And I can do the same thing for the input, okay. Differential in A, maximum and the minimum. Here I'm using those two terms. Then I can calculate my ADM. So I've got all these equations pre-written which can give me those numbers. So let's just pop them in and see how it works. So I'm going to copy this one first. I'll copy it to the clipboard. Trace, evaluate. 386 millivolts. Peak to peak coming out. Okay, let's look at my input. 20 millivolts peak to peak. Let's calculate my ADM, and again you can see I've formulated these quite quickly inside Notepad. 19.34. Well, this is the expression that I want to use to optimize to then calculate the value of RD. Now there's a couple of ways I can do that. Inside this circuit I can do an advanced simulation, or I can optimize based upon that transient simulation, extracting that value. The easiest thing for you is just to tweak that value of RD and then see what happens from there. Okay, I'm going to sweep RD and get a family of curves and get some numbers off it. So the easiest way inside this tool at the moment, transient, parametric plot. Okay, we're going to change the global parameter RD, going to change it 38 ohms, 42 ohms in 1 ohm steps. Run PSpice. Now you notice that the simulator's actually got several outputs here. It's got RD at 38, 39, 40, 41 and 42, so it's got a lot of outputs. When we plot them, we're going to get what's called a family of curves on here. What I'm now going to plot is this value, which is ADM, trace, evaluate measurement. We've now got all of those values there, look. Okay, so we can see that when we went down to our first value, which would be 38 ohms, we're at 19.9, and then we started to diverge. We've got further away, so we want to go lower than 38 ohms. Okay, my guess is 37 ohms is going to be about fine. Parametric, global parameter, RD, 36, 41 steps. We now have a family of curves plotted. Okay, and now we will evaluate our differential gain. 20.5, 20.2, 19.9. So this value here is almost exactly where you want to be. You could get a little bit more accurate by optimizing. I think I'll stop at that one. That'd be 36, 37, 38 ohms. Okay, so I've optimized this value now for 38 ohms. Okay, that one's set. The only thing I now need to do is to optimize RDC1, and I don't need to do a transient simulation for that, so I can go back to bias points. What we're going to do now is we're going to optimize RDC1 to get V out equals 0 volts with no input signal. So our new signal is a bias point. Click apply, click OK, simulate. Back to here, we can see that we're at 356 millivolts at this node. We actually, hang on, no, we're at minus 37 millivolts at this node. So this is the voltage that we need to reduce by increasing our DC. So let's go to here, DC sweep, global parameter, RDC. At the moment it's 786, so why don't we go 700 ohms to 850 ohms in 1 ohm steps. And what we're looking for is the voltage at V out. We're not looking for anything else. Plot. And we've got a nice linear plot there. We can see it crosses 0 around here. We'll use our trace evaluate measurements and we will find the voltage X at width N. We want V out. Okay, we want it to be 0 and we want the first occurrence of that. 710.67, so that's 710.7. Change the simulation, back to bias, click apply, click OK, off we go. Back to the circuit, minus 11 microvolts, bingo. As far as I'm concerned now, the circuit is designed, the circuit is optimized. There is only one thing left to do. I want to measure the differential mode gain, the common mode gain, and the common mode rejection ratio. So these parameters are my final parameters. I'm going to pop those numbers into my my presentation. So RT 93.94. Okay, let's just minimize that one. RC hasn't changed, it's still stayed at 2600 ohms. RD has changed, it's now 38 ohms, but we know we could get a little bit better than that, but never mind. RDC is now 710.7 ohms, and our degeneration didn't change, that stayed at 450. Again, it's not necessarily a crucial component on there. Our current source reference resistor 137.6 ohms did change. So now we've got our optimum values, so just kept a track of those. Now what we'll just do is we'll measure ADM, ACM, and we'll see how well this circuit performs. So our simulation is now going to be a transient, 10 milliseconds, 5 microseconds reference. Okay, we're going to measure the differential signal coming in and the differential or the common signal going out. Okay, simulate. I can go straight back to my my notepad, because my notepad has already got this calculation here. ADM, Control C, plot, trace, evaluate. Okay, 19.94. So let's put that back in here. We have measured 19.94. Now let's measure the common mode gain. Okay, so I'm going to close the simulator there, go back to here. And this is why I've got this circuit here. I can change this wire and change the label to COM A, and I can change this wire and change it to COM A. So now I'm putting the same signal in and I'm looking for the difference, or I'm looking for any signal coming out, okay, because there shouldn't be any signal coming out. So again, it's V out down to 0 and it's also common down to 0. Notice as well here I've cheating a little bit. I've added an extra bit of signal coming in. So my amplitude's 100 millivolts, not 10 millivolts. Let's run the simulation. Simulation should be fine like that. Let's go. Okay, let's just add a trace. We would be interested in the common mode signal coming in and the output signal. Okay, The common mode signal coming in is 200 millivolts peak. The output signal is tiny. Let's just delete the input signal. There's the output signal. Very, very small. Now let's go to my tool. Let's measure the output voltage. Okay. The output voltage is 620 microvolts peak to peak. Let's measure the input signal. (200 millivolts). Okay, and now let's get the ORCAD tool to actually calculate the whole lot. So this is ACM, common mode gain in this design. Let's delete one of these, we don't need it. Okay, let's add that one in. So it's doing everything in one. 3.13 milli gain. Okay, that is a serious attenuation. So let's write that down. What was the value? 3.1 milli. Okay, as the value of gain. So let's put these two numbers in. Common mode rejection ratio is 19.94 divided by 3.1 e minus 3. Okay, and what does that come out to? Well, I've already got a calculator ready to go here. This is Speed Crunch, one that I like. 19.94 divided by 3.1 e minus 3. 6,432. Okay, that's a lot. 6,432. Let's put that into decibels. Okay, so we want 20 times the log to the base 10 of that, 76.2. Okay, job done. We've calculated the gain, we've calculated the common mode gain, we've proven that we were close to 20. We're not perfect at 20, but we're very close. We've calculated the common mode gain and we've calculated the common mode rejection ratio. So that's the whole design complete. Go back right the way to the beginning of what we actually set out to do. Okay, we have designed all components on there, we've optimized them, and we've performed our DC sweeps. So hopefully that should help in being able to solve these puzzles.